Now, we are talking about pulse widths because we are going somewhere with it. Now, we can also consider another measure, probably a more robust measure, in which case we consider the pulse as a distribution. Actually, we should consider this as a distribution of energy in time, right. So, as a statistical sort of distribution. So, we consider little segments of the pulse in time, okay. Almost think of it like a histogram of whatever type. All right, and then calculate the moments of this distribution. Okay. So, the RMS width of a pulse is per definition the second moment of the pulse normalized again to the, what is f? F is the amplitude. So, normalized to the area under the curve for this pulse. Okay. That's important. Well, okay, we have not told you what the vertical axis is, whether if it's field or intensity. If it is intensity, if the vertical axis is intensity, this is the energy contained in the pulse. So, also here we can always define the width in terms of the intensity amplitude, intensity envelope or the field envelope. The discussion I had earlier pertains to the situation when this is the intensity envelope. Okay. If this is I, then the area under the curve is energy. If it is field, then it is something else. So, we have implicitly assumed that this is a intensity dependent quantity or it is the intensity envelope. So, the RMS width is another measure where it is essentially the normalized second moment. Yeah. So, what is the problem with this measure for the pulse? Okay. Well, first of all, what is the motivation for this sort of a measure? The motivation for this measure is, statistically speaking, it is what can I do about when I have distributions. The way to think of distributions is to calculate the various moments of the distribution. It looks nice when I sketch a Gaussian pulse like this. It probably looks very nice. But the problem is, in real life, you do not even know what the shape of the pulse is. Gaussian, secant hyperbolic, distorted stuff, whatever not, right. So, if that is the case, if that is the case when it comes to the pulse, then the moments are the distribution. The more you want about details, the higher the moments you need to compute. This is actually going to be true when we think about measuring pulses. Indeed, we will have to think about the higher moments, right. So, the point here is that the first moment gives you pretty much nothing if we consider this to be the intensity. If I integrate over everything, which is not the first moment, you can say the 0th moment, it is just the intensity contained in the pulse. Okay. Whereas t times f of t would be the first moment, that is the mean. Okay. So, what we are considering here, but we know that is the mean. Here the second moment of the distribution is what we are considering the RMS width. The good thing about it is when we need to deal with the math, integrals are easy to do analytically, but maybe that is, you can say, not so much our concern. If you cannot do it analytically, just do it numerically, it is just as fine. But the issue, the real other issue is that it weighs the wings of the pulse more than the center, because t takes a smaller value here close to the center and t square grows, or I should plot it maybe like that. So, the information which you get by determining the second moment, but that is what you want to do in statistics, that you essentially get the wings weighted quite a lot, right. The t square function tends to, if you think of this as an integral weighting weight, it's a weighted integral of f of t, then you essentially tend to have a lot more of it, of the weighting on the wings of the pulse, which is okay, where actually information lies in the entire shape of the distribution. So, normally we would say that is fine, but the problem that we face is that a Gaussian or these sort of distributions actually never go to 0. We can at best consider these as falling below the noise level of detection on the wings of the pulse, right. On these wings, it is going down to the noise level. Now, it is okay to define a distribution, but how are you going to measure this in real life? Because if you can't measure the RMS pulse width, or it becomes challenging, or it takes a PhD to do a few of these, then it is not a good measure, right. You need a different measure for things. You can compare this to doing the census of a country of like ours, 1.4 billion. To get the most accurate data, if everybody speaks the truth about the numbers, then the best and most accurate way of doing the measurement would be to literally have every person interviewed for the census. But that is going to take you, if you plan to do census every 10 years, if this is the process itself, okay, maybe in the digital age it could be more efficient, but even so, if the process takes a better part of 10 years, then it is fairly meaningless. So, if we want to take a sample, we want to sample, the process has to be also efficient in terms of a real world implementation. So, here in order to do a real world implementation, the problem arises that this forces you to do measurements in areas where the amplitude of the pulse, whether you consider intensity or field profile, is pretty low, tends to go down to the noise level. So, therefore, this measure can have a challenge, but having said that, it is often important to also know the profile of the pulse even on the wings, because you remember we had a discussion about the fourth order chirp. What does fourth order chirp do? It adds wings to an otherwise cleaner pulse. So, there is information there, but do you always need it? Do you always want to care to measure it is the question. But notionally, whenever we talk about pulse width, this is what we are going to mean, or we are going to be brainwashed to mean, if we already haven't been. I have already been brainwashed to thinking that the full width at half max of a pulse, full width at half maximum, is the pulse intensity, you see. But we have been using this definition. For example, when we wrote down a Gaussian amplitude function of a Gaussian pulse, we wrote this to be e to the t squared by tau g square and so on. You recall this? So, here tau g was full width at 1 over e. Instead of half maximum, we said 1 over e. Okay. But 1 over e is 2.7 something. So, it is not very different from a half maximum. Of course, half maximum is also just a choice. So, this is what we are going to mean, but herein it becomes very important to understand the caveats in defining this as a measure. This is a pretty good and robust measure to maybe compare pulses or compare distributions. We always do this in the case of scenarios like a Gaussian distribution, right. But then the point being that this ignores anything that is below the half maximum. such a measure of a half maximum to take a pulse. This is the t axis. Now, all you care is maximum, okay, maybe, and half maximum. If, as is shown in the figure here, if I had a method, if I had a FWHM meter for a pulse, if I can devise such a thing, then it is going to even if it faithfully records at full width at half max, if the pulse has satellites. Where do satellites come from? Say the pulse propagates through a third order dispersion, medium with a significant third order chirp. Okay, the pulse is carrying a third order chirp or a fifth order chirp. We know that this creates satellites, right? Such the spectral, it's up there after all expansions, Taylor expansions of the spectral phase function. So then it ignores these, this measure ignores, I mean a pulse, a neat Gaussian pulse, perfectly an unchirped Gaussian pulse, or it may even carry a linear chirp. Of course, these measures are not at all chirp sensitive, but then if I consider a pulse with 0 third order phase spectral phase coefficient versus something with a significant third order spectral phase coefficient, we could have the FWHM meter read almost the same, which is a problem because in some sense the width of a pulse is supposed to reflect the a measure of how the pulse energy is concentrated in time. Is that happening? Well, we should ask ourselves and answer. So, if we had say pulses with some satellites, which by the way lasers can produce, like for example a Q switched laser does normally produce some satellite pulses. Do we like the fact that satellite pulses are produced? Probably not. Probably we do not like the fact that pulses have these, lasers produce these satellite pulses. So, then we would want to suppress them, right. Pulses not can, they always ride on a pedestal. If this is say 100 femtoseconds long, this pedestal could even be 100 picoseconds wide. FWHM totally ignores this. Actually, a lot of pulse width measurement techniques that we are going to talk about do ignore this measure because of the following reason, which I will state, just go about stating without much ado about how we measure it and stuff like that, is that then the vertical scale also comes into picture and becomes important. So, let us consider this even on a logarithmic scale. I will have to break the scale to give you a real good idea, but the point being that if on whatever vertical scale units, if this is a factor of say 1000, this maximum appears in the scale on factors of thousands, then the pedestal would be about 1 to 10. So, we can describe for pulses a quantity called peak to pedestal ratio. So, if you are going to procure a femtosecond laser to do attosecond science, you will want to know this from a vendor. So, the typical laser systems which come out of chirp pulse amplification technology have peak to pedestal ratios of 1000 or a 10,000. But so the dynamic range of a detector that you want to use is very unlikely going to be, you are going to be able to do the pulse width measurement and the pedestal measurement with the same metrology device. Okay. Having said that, FWHM is a very realistic thing to measure in a lab. If I know that my laser produces pulses with a peak to pedestal ratio of 10 to the 3 or 4, right, then I take it, okay, and make the most of it in life, so to say. Once I know this about my laser, and I know that it is the same laser, it behaves well, then all I care about on a day to day basis is to get a measure for FWHM and then use such a laser system in my day to day use. That is the spirit in which we do measurements of pulse widths. Okay, how we are going to do this is another question. Again, that thing will haunt us. If these are the shortest events, then what is the way out, right? So, let us keep that mystery up for a while. We will, because we are not going to answer that question today. Now, the whole point about tickling this sleeping animal, which is always a point, like we spoke so much about pulses in this course without even like ever answering the question, how are you going to measure anything at all, right? Is this a course on, otherwise it becomes a course on just Gaussian pulses and whatever. It's mathematical, it's a mathematical exercise at best, right? We will come to that solving this mystery soon enough. Even for doing that, we need more to learn more about what we are going to discuss in this lecture and the next. So, they are indeed quite important. So, even before, since we have developed things as far as we already have, and we are now good at Fourier transforming stuff, we can try and get some very good understanding of things using this iconic uncertainty product, which in common parlance is considered to be the legacy of the foundational aspects of quantum mechanics and Heisenberg's uncertainty principle. Indeed, it predates such an aspect, because it became a famous thing in physics and elsewhere as a Heisenberg uncertainty principle, because it was applied to matter which is not expected to have any wave nature, so to say. Whereas, for waves which are say waves and pulses, this is just a Fourier relation between a pair of Fourier conjugate variables t and omega or t and nu. So, consider a width, any measure of the width, keep it consistent in the time and the spectral domain, the two conjugate domains. Let us use the effective widths in both cases. Delta t, the effective width in the time domain, delta omega, the effective width of the Fourier transformed spectrum, the spectral function, capital F of omega in the frequency domain. Then we can essentially arrive at certain very useful relations, which is to say that we can arrive at a lower bound for this measure delta t, okay, by considering the following. The 0 of the scale in the temporal and the spectral domain is identified with the maximum of the distribution, okay. The 0 of the scale, watch out for this. The 0 of the temporal or spectral scales is identified with the maximum of the distribution in either domain. If so, then a lower bound for these widths, okay. Let us consider the delta t, the effective width in the time domain, sorry, the time domain. Is as follows. The effective width in the time domain, which was normalized to the maximum value that the function attains, which is f of 0, okay, is defined as follows. Now, essentially compute this integral, okay, if I compute this integral which is f of t exponent of minus I 0 times t, where instead of omega I take a particular frequency 0 and compute this integral. All we are saying is that this true effective width, which is given by this integral over all of time, if I now compare it to the Fourier transform like integral of f of t, this is actually, you can say, the value of the Fourier transform at 0, because it is 0 times t. This entire thing is just unity. I am writing 1 like this and reinterpreting this integral as the value of the Fourier transform at omega is equal to 0, right. In other words, if I had omega here instead of 0, if we had omega here instead of 0, this integral would have been the Fourier transform. So, this would have been f of omega everywhere, whereas the value of, then we replace this with the value of the Fourier transform at omega is equal to 0, divide this by f of 0, the maximum of the pulse in the time domain. So, the ratio of the two maxima presents a lower bound for the effective width. The effective width cannot be smaller than this. Turn this around, the argument around, and apply the same in the frequency domain. Again, take the integral over the absolute value of f of omega. Take this around. In fact, here we are dropping the absolute value. So, it will necessarily be lesser than this total integral, right. Once again, treat this as computing the inverse Fourier transform and affixing the value of it at time t is equal to 0, which is the, for distributions of the kind that we have considered, this is essentially going to be the maximum value of the temporal maximum of the pulse. Then we now just show that the width of the effective width in the omega domain as a lower bound, which is 2 pi times the ratio of the distributions in the temporal, the maxima of the distributions in the temporal versus the frequency domain. Now, after all, this is an uncertainty relation of product that we are interested in developing. So, these uncertainty products are delta omega delta t, delta nu delta t, and so on. The factor of 2 pi arises out of the fact that we have omega there. So, combining these two results, delta omega delta t, this product of what? Product of time. When we say time, the temporal width, and when we say omega, omega the bandwidth, the spectral width, the product of the time width and the spectral width, or the time bandwidth product, is necessarily always greater than 2 pi times little f of 0 divided by capital F of 0 multiplied by capital F of 0 divided by little f of 0, or we tease out the uncertainty relation, so called uncertainty relation. What is the uncertainty here? It is just two widths. The product of the temporal width and the spectral widths is always greater than 2 pi when we consider t and omega. So, this is the time bandwidth product. It is at best 2 pi, or delta nu delta t, cyclical frequency and temporal widths is at best unity. Okay. So, this just tells us that such uncertainty relations can be derived also for other definitions of widths, whether it is the RMS width or the FWHM. The right hand side may vary, but the manner in which we have defined the delta u or the delta t notwithstanding, we will always have an uncertainty relation like this, because all the three quantities are linearly related. The effective width, the RMS width and the FWHM width, or any width that we may choose to invent tomorrow, if it still keeps itself to the meaning of the word, a measure of width of the pulse. All these must be linearly related, right? They are all measuring something related to some measure of the pulse, by which, I mean, even if it's belaboring this a little too much, if this is my pulse, the width I can measure, and the width I measure has to have something to do with the pulse. I put a belt, the measuring tape can be put around here, the measuring tape can be put around here, the measuring tape can be here, wherever, right. This has nothing to do with weight loss, it is just a good measure. Everybody, every practitioner may have a reason for a good measure. Measuring a pedestal means we really want to take something very close, a very higher order moment, whereas the others are all about the various different moments of these distributions. Okay, so that's that. So an uncertainty product is a hallmark of the Fourier relation between the time and the spectral domain. You can define something identical in the spatial domain between a delta k and a delta kx as well. So all this arises out of the well known definitions of Fourier transforms, which we have been using